Okay, welcome back everybody. This is our second video in atomic structure. And today what I'm going to attempt to do is try and, show you how physics and how understanding the nature of light and the nature of matter um, and all of their properties will help us to get a better understanding of the atom. So far what we've gone through is how you have the atom as containing a positive nucleus with the electrons outside. But there were some issues with what Rutherford was saying. One big issue was, well, what's going on with these electrons? They're negative and they're outside the nucleus, and you have a positive nucleus. Why aren't those electrons just, falling into the nucleus? How are they able to stay outside of the nucleus? And so in order to answer that, we need to do a little bit of background, and we need to talk about the nature of light. And when we look at light, we think of it as, traditionally being a wave. And we can explain a lot of the properties of light when we look at it as a wave. How does light, for example, bend around corners? If you wear eyeglasses, how is the light from, outside focused into your eye so that you can see? All of these are wave properties of light that are being manipulated. But in the early 1900s, some really, really brilliant scientists, Maxwell Planck, Albert Einstein, Niels Bohr, they started looking at light for its particle properties and starting to use those particle properties to explain how the atom worked and how the electrons in the atom behaved. So let's talk about the wave nature of light. So, when we have light, we look at it as, this wave, and I'll show you a picture on the next page. If you want to skip ahead, you can see that here. This is what the wave, a light wave, looks like. Probably have seen pictures like this before. But when we look at light as a wave, we want a way to describe it. For now, when we talk about light, we usually refer to the visible form, although there's other forms of light that we can't see. Infrared, ultraviolet, X-ray, microwave, and I'll show you a complete electromagnetic spectrum in a few minutes. Now, electromagnetic radiation, it's a form of energy. It's carrying it through space. Sometimes people call it radiant energy. This electromagnetic radiation, it will travel at a constant velocity, and that velocity is 3 times 10 to the 8 meters per second. But that's really only through a vacuum. In reality, if light were to hit something else, like it were to, hit water or hit air, it'll slow down. And so when light hits air or hits water, it actually will slow down, and you'll see those light waves bend. So if you've ever done this trick where you've taken a straw or a pencil and you've put it into a beaker or into a glass, and you see that it looks as though there's some sort of disconnect between the pencil, like it got chopped, that's due to light waves bending and slowing down when they hit something different than a vacuum or something different than air. Now you need to be able to describe the characteristics of a wave, and so it has these set features, and I've underlined them here: wavelength, frequency, and amplitude. And we'll go through what each one means, and I'll show you that on the picture. But what's important to know is that the wavelength and the frequency are related through an equation, which is c equals frequency times lambda. And so c is the velocity or the speed of the light, f is the frequency, and lambda is the wavelength. And so you can also write frequency as this little script v here. But what's really important about this equation is that the frequency and the wavelength, they're inverse. As the frequency goes up, the wavelength goes down, or vice versa. I also get the question, what does C mean? Why don't they just use like S for speed? And so C is actually stands for the Latin term celeritas, and that means speed in Latin. So let's look at what a light wave looks like. And so here I have these pictures of different light waves. And so on this, I show you what the wavelength looks like, and the wavelength is defined as the distance between two peaks or between two troughs. The amplitude is the height of the wave. So how tall is the wave? And what the amplitude really corresponds to, it corresponds to the brightness. The wavelength, what it really corresponds to, is the color. Now, I could change the wavelength, and I'll change the color. And so here I have a wavelength that is shorter. So how does the frequency tie into this? Well, the frequency is given the unit cycles per second. So a way I like to visualize this is imagine that you're standing here on the wave. And the wave is passing underneath you. Well, how many cycles per second pass underneath your feet? What we can see is that when the wavelength is half, the amount of cycles per second would double. You'd have twice as many cycles passing under your feet per second. That is why they're inverse. If I decrease the wavelength, then I increase the frequency. So look at these two waves here. So which one of these has the shorter wavelength? Which one of these has the higher frequency? So take a look, answer those questions. Let me know, we'll talk about it tomorrow in class. So I promised you that I would show you the electromagnetic spectrum, not just the visible spectrum. And this is the entire electromagnetic spectrum for light. What we can see is within the visible range. This is what we're able to detect with our eyes. But there's other forms of electromagnetic radiation or light that we can't see. So we have ultraviolet light, X-rays, and gamma rays. And these at this end over here, these tend to have shorter wavelengths and higher frequencies. At the other end of the spectrum, we have infrared, microwaves, radio frequency, and those will tend to have longer wavelengths and lower frequencies. We'll talk more about, how this relates to the color and how to find each of these, and we're going to do that actually by using the equation where we have C equals frequency times lambda. And we'll do some practice problems with that, and you'll see how those relate. So let's talk a little bit about the particle nature of light. So far what we have is this wave property of light. Well, how is light behaving as a particle, and what does that mean exactly? So it turns out that scientists, specifically Maxwell Planck, P-L-A-N-C-K, was studying the nature of solids that were completely black. Things like graphite, things like coal, things like metals that are completely black. And he would heat them, and he would see what would happen, what radiation was given off. And what he saw was that the energy given off was weird. It wasn't where, it could be explained using some sort of wave property of light. It's almost as if the light coming off of these solid black objects when they were heated were little chunks of energy. And so Planck came up with an equation that would describe this and explain this. And this is his equation right here. Energy equals H, which is his constant, which I define below here, times the frequency. Now, these little chunks, these little quanta, as he called them, or what we know as photons, the energy of an individual photon is really, really tiny. They're very, very small. Look at his constant. His constant is like this really, really small number. So we necessarily don't notice it. It was something that took really careful experimentation. And in fact, Planck had this idea, this black body radiation as he called it, and he had the equation to go along with it that described the energy coming off of these objects. But he didn't really know the full extent of what he had discovered. If we look at an example of black body radiation, this is hot molten iron being poured, and you can see the heat and light being given off by this. And we can use his equation, E equals Planck's constant times the frequency, in order to determine the energy coming off. But really, he wasn't, exactly sure. He didn't have this kind of, great evidence and, this great ability to explain what he found. And that really came through with Albert Einstein. What I want to do before then, though, before we talk about Albert Einstein, is I'd like to do a couple of practice problems. And so this first question says, we have a light laser. It has a wavelength of 300 nanometers. What's the frequency? So we only have two equations that we can use. One is C equals frequency times lambda. The other one is energy equals H times frequency. So we have to determine, which one are we going to use? Well, they give us a wavelength, so this is my lambda, and they're asking me for the frequency. Since I have the wavelength and I want the frequency, I'd probably go with this one up here. So now, my C is equal to 3 times 10 to the 8, and that's meters for every 1 second. This is equal to my frequency times my wavelength. My wavelength is 300 nanometers. The problem is with the units. This is in nanometers, this is in meters. It won't work where they cancel out. So I need to figure out how to change nanometers to meters. So I can make this into meters pretty easily. For every 1 meter, there's 10 to the 9 nanometers. So if I have this in the right units, I have 3 times 10 to the 8 meters per second equals frequency times 3 times 10 to the negative 7 meters. Now if I solve for frequency, I'll get frequency equals 1 times 10 to the 15th, and that'll be cycles per second. Now you'll also see frequency written as hertz, so this is 1 times 10 to the 15 hertz. Now I'm being asked, well, what's the energy in kilojoules of this light? So let's see if we can figure out that. We have energy equals H times frequency. Well, now we have the frequency, 1 times 10 to the 15th. And we can times it by 6.63 times 10 to the negative 34th, that's Planck's constant. And we can come up with our energy, and that will be in joules. If we look at the units for this, this is joules times seconds, and this is really 1 over seconds, or cycles per second. So the seconds will cross out, and I'll be left with joules. So now if I do this, I will get 6.63 times 10 to the negative 19 joules, and that will be 6.63 times 10 to the negative 22 kilojoules. So the energy that the light has, I have a 300 nanometer laser, will be about each photon in there, each quanta of energy, each particle of light or packet of light will contain around 10 to the negative 22 joules, or kilojoules. Now the thing is, that doesn't seem like a lot at all, but imagine a stream of light particles. There are so many of them that this could be quite powerful. Now let's go back and talk a little bit about what Einstein did in order to really talk and understand what it means to have particles of light. His famous experiment is called the photoelectric effect. This effect can only be explained if you are treating light as if it was a stream of particles and not just waves. What did his experiment do? It was really kind of simple. What he did was he shined light that was a single color, monochromatic, on the surface of a metal. And he started changing the frequency of the light. And what he noticed was that if he had light with a high enough frequency, the energy that would come in could cause electrons from the metal to come off. It was that simple. This is sort of a really simple representation of it. You shine light in, electrons come off. But what he noticed, which was what really sort of bolstered Planck's idea, was that it was the frequency of the light. And he started messing around with the frequency. What if he, for example, used a higher frequency? Well, then he would see that the energy of the electrons were greater coming off. And if we go back to Planck's equation, E equals hf, it makes sense. The higher the frequency, the higher the energy of the photons, that should hit the electrons with more force, and those electrons will come off with more energy. If he used a higher intensity, what he noticed was that there would be more electrons. And what's really important is that any light below the frequency would fail to eject electrons. So we have these three key findings here. The intensity would give more electrons. The frequency, the higher it was, the more the energy of the electrons were that were ejected. Any light below the minimum frequency would fail to eject electrons. And what's so interesting about this is that if light was just a wave, it would be the intensity, how bright the light was, the amplitude, not the frequency, that was really crucial. Think about it, if I had dim light here, dim light would have a very low amplitude. Bright light would have a very high amplitude. If it was just light as a wave that was so important to this, the brightness would play a key role. But it didn't. It was the frequency. And so let's draw out, particle-wise, what's going on with the photoelectric effect. Why is this working? Well, let's say that you have red light, low frequency. Let's think about light now totally as particles, and we'll draw little particles like this to show the photons, the particles of light. So if I have red light and I have my metal surface here, the particles will come in. Now, if I'm a dim intensity, I won't have a lot of photons. This will be few photons. Since it's low frequency, it means that the photons are low energy. So these photons will come in, they will hit the metal, but we'll get no electrons ejected. So no electrons are ejected. And a way of thinking about this is that each photon that comes in, so if I have one photon, that one photon will come in and it will interact with one electron. And that's really important. Since each photon has such low energy, no matter how many photons you were to, aim at the metal, none of those photons would be powerful enough to eject an electron. If we do high intensity light, well, now instead of having just a few photons, we'll have a lot of photons. And so now over here I drew 1, 2, 3, 4, 5, 6, 7, 8. Now I'll have 20. And so these photons, they will come in, and there's a lot of them now. But even though there's a lot of photons and the light is really bright, no electrons are ejected. Why are there no electrons ejected? Well, remember that one photon will interact with one electron. So a lot of photons, they'll be hitting that metal, but none of those photons will have enough energy to eject an electron. Now, just as like a side note here, if this was a wave, properties of light that we were looking at. The red light over here, the low frequency and low intensity wavelength, intensity light, the dim light, this would have a small amplitude. Whereas the high intensity light would have a high amplitude or a large amplitude. So if it was the wave properties of the light, then the amplitude would be very important, and you would expect to see that high intensity light, high amplitude light, would in fact give you electrons being ejected, but we do not see that. It doesn't matter the intensity of the light, because light's behaving as a particle, and those particles, each one of them, since it's one photon for one electron, they do not have enough energy to eject an electron. Let's go over to violet light. Now violet light's high frequency, so that means high energy. Low intensity, again, would be just a few of the photons. So if we do that over here, and we copy this and we paste them, well, now we have the same photons coming in, except now they're high energy photons. And so when we have those high energy photons coming in, they hit the metal, and because they're high energy photons, electrons are ejected. If we go high intensity here, we still have high energy, but now we have bright light. So now we have a lot more photons. If I draw that over here, now I have a lot more photons. So now those are all coming in, they're hitting the metal. When they hit the metal, the electrons are ejected, but now we have more electrons ejected. So over here we have a few electrons ejected. Over here we have a lot of electrons ejected. But something important is that they have the same energy. The only thing that will change the energy of the light and the energy of the electrons ejected is the frequency or the wavelength of the light. All that the intensity does is it adds more photons, more particles of light. More photons, more particles of light means that the energy of the light doesn't change, just the number of photons change. If I have more photons, but the light is low energy, it doesn't matter. You'll never eject electrons like we show up here. If you have a situation where in fact the light does have enough energy and you shine brighter light on it with the same color, well then you're going to get more electrons coming off. Now why is this so important? Why did I take 10 minutes of your time to explain this to you and go on this sort of like side tangent? And it's because we're going to apply this to the atom. The idea is that when you shine light on an atom, or when you add electricity to an atom, or when you excite an atom, that the photons, the energy that you're adding, is able to interact with electrons in the atom, and it's able to get them to either gain energy or lose energy. There's a transfer of energy between the electrons and the electrons in the atom. So what Bohr did, the new model of this atom, this you learned in 7th grade, you learned about energy levels. He used the idea of photons, the idea of quantized energy, to say that the entire atom is quantized. Remember, in class we talked what was the problem about Rutherford's model. And the problem with Rutherford's model was in fact that he couldn't explain why the electrons were not, being pulled into the nucleus. Well, Bohr said because these electrons are in orbits, stable orbits. And the only way that they can move between orbits is when you add energy to them, when they absorb a photon of energy, and they use that energy that they absorb to jump to higher levels. Here are the ideas behind his model. Electrons are in orbits of certain radii. Those correspond to certain energies. So if I were to have, my nucleus, I would have an electron in an orbit around it. This electron is in this permitted orbit and it has a certain amount of energy. Now, if a photon comes in, so here's my photon coming in. This photon can come in and it can be absorbed by the electron. And what will happen is this electron will now jump up to a higher energy level. If the electron goes back down to the ground state, it will then release that photon in the process. You can see these photons being released because you can see the color of light being given off by an atom when it returns back to its ground state. So an electron can only absorb photons of energy, and it can use those photons of energy to jump between energy levels from one state to another. It can only jump between allowable orbits. This was Bohr's model, and if you want to see, well, hey, what does it look like? What does it look like when an electron releases energy? So if the electron didn't have these allowable energy levels, these orbits, you would see this sort of rainbow effect being given off by atoms that were excited. But instead, what you see is these individual lines. Each one of these colored lines here, and this and here, they represent a transition, a movement of an electron between a high level and a low level. The energy given off was exquisitely described by Bohr. He was able to predict these colors being given off by hydrogen almost to the nanometer. And that's because he knew that energy is quantized. He also knew that the atom could absorb this quantized energy and that the atom itself was quantized, meaning that the electrons had specific energy levels, and that those electrons could only be in those specific energy levels and move between them. This series of spectral lines here is called the Balmer series. Change the color. Balmer series. And this is when an electron returns from an energy level, which will give the symbol N of high, to an N that's lower, level 2. So whenever an electron returns back to energy level number 2, it gives off visible light. There's other series too. And what this next slide shows, which is where I'm going to stop, is how the electron can move between these different energy levels. Over here is the energy level. Energy level 1, energy level 2, energy level 3, 4, 5, 6. And when an electron moves between those allowable energy levels, those shells, those orbits, the electron will release energy when it goes from a higher to a lower state. Now, we're not going to do the math for calculating that, but Bohr was able to calculate the math. And like I said, he, in explicit detail, was able to predict these colors, these specific lines. We'll do a lab with this. My next video will pick up with reviewing Bohr, and then we'll talk about the next model of the atom after we talk about Bohr, which is the quantum mechanical model.